Let's have a look at the Ricci Tensor and Scalar, otherwise known as the Curvature Scalar. So we'll look at a way of deriving the Ricci Tensor and the Ricci Scalar, making use of the symmetry properties of the Riemann Tensor. So from a previous video, the symmetry properties were calculated to be these three here. What we're going to do is, by contracting on pairs of indices, we're going to reduce the order of the Riemann tensor and create a new lower order tensor, second order, known as the Ricci tensor. So starting with the first symmetry property from the last video, we start here. We're going to multiply through by the inverse metric to raise some indices, to raise an indice, in this case alpha, the first index. When we come down to that, we get down to this line here, this statement here. When we contract on the first and second indices, we end up with this statement here. And that can only be true if the contracted tensor is equal to 0. And so when we contract on the first and second indices, the Riemann tensor goes to 0. Now trying the second symmetry relation. This one here, again multiply by the inverse metric so that we can raise the first index. And a similar thing to the last case happens when we contract on the first and fourth indices, the Riemann tensor, we end up with a result that doesn't make sense unless the contracted Riemann tensor goes to 0. And so in this case and on the previous page, we don't get much information because the Riemann tensor goes to 0 when it's contracted on the first and second and on the first and fourth indices. The third symmetry relation up here, again multiply through by the inverse metric to raise the first index, to raise the alpha index. And what happens when we contract on the first and third indices, in both cases we end up producing a new tensor. It doesn't go to 0. It's the only contraction that does not. And we end up with this second order tensor here, which appears, by the placement of the indices, to be symmetric. So we'll investigate and see if that's the case. In the last video we found this arrangement here where the Riemann tensor had the last three indices permuted, mu, beta, gamma, mu, gamma, mu, beta, three different arrangements of them, and the tensors then summed, gave us 0. So let's take that whole relationship and multiply through by the inverse metric to raise the first index alpha. We end up here. We then contract on lambda, the raised index, and beta. Lambda, beta there, we contract on them, they both become lambda. Now, this second case here, contracting on the first and third index, sent the contracted Riemann tensor to 0. So that went to 0. Before contracting here, if we use the symmetry properties and alter the position of mu and lambda, then we'll be contracting on the first which makes it negative from the symmetry relations. But if we then contract on the first and third indices, we end up with this object here. So over here, contracting on the first and third index gives us the Ricci tensor with mu and gamma as indices, and over here gives us the same tensor but with the indices reversed. And we're told that these two then go to 0, which implies that R mu gamma is the same as R gamma mu, that the Ricci tensor, or this new second order tensor, is indeed symmetric. A couple of index manipulation rules. The Ricci tensor R mu gamma, multiply through by the inverse metric. The mu's cancel out here, they're summed out. We're left with R alpha in the contravariant position and gamma in the covariant position, or alpha in the raised position, gamma in the lower. The symmetry of the Ricci tensor means that these can be reversed, that the order can be reversed, or we can show through this that, again, multiplying through by the inverse metric, the mu cancels out, we're left with alpha. So these two things are equal. The second order tensor Ricci, multiply through by the inverse metric with the same indices, sums it out, and we're left with a scalar. Again, the order reduced by 2, we're left with a scalar, and also the inverse metric multiplied with the metric gives us the Kronecker delta function. Next we'll have a look at the Bianchi identity found in the last video, which is this here. And we know that when the last three indices, mu, beta and gamma, are permuted, rearranged with the covariant derivative, we end up with this relation, the Bianchi identity. We're going to use that to derive a new arrangement of tensors, a new object. So here it is, the Bianchi identity again. Multiply through by the inverse metric with alpha as its first raised index. That raises alpha, replaces it with lambda in all three cases. Next job will be to contract lambda with beta to end up with this arrangement. Lambda, beta, and lambda and beta here, we end up with that arrangement. We know this contracts down to the second order Ricci tensor here. This object stays the same. This object here, we've used the symmetry properties to rearrange it to get lambda out of the fourth position there, put it in the third position because we know it can then contract down. That puts the minus sign here. Come down to the next line, and contracting on lambda gives us this object here. Next step. Multiply through by the inverse metric again with mu and delta as its indices. Here we go, that's just from the last page, this bit inside the brackets. When we do that, we get rid of the mu, put the delta up there, raise the mu, put the delta up here, get rid of the mu, put the delta up here. Next thing, we're going to contract on delta and gamma, contracting on delta and gamma, delta and gamma, and here we're going to delta and gamma here, here we go. Next line down, we notice that we have lambda, and we have delta and delta. Now, what happens here is that the lambda and the delta are just dummy indices, so it doesn't matter, because we're summing them out, it doesn't matter what we call them. We can call them any symbol we like. So we might as well call them all lambda, or call them all delta. In this case, we'll call them all lambda. We use lambda because it really doesn't matter. When they're summed out, when they're together like that, one up and one down, they're the same, we're summing them out. And so we might as well just call them lambda, which is what we do here. So we get the covariant derivative of the curvature scalar or Ricci scalar with respect to mu, the index nu here, lambda here again. We get two lots of these because then they're the same. Next page over, multiply through by -1, then divide through by 2. Factorise out the common delta lambda here, the covariant derivative with respect to the index lambda, that comes outside here. And over here we make use of the Kronecker delta. This will go to 0 unless nu and lambda are equal to each other. Multiply through by the inverse metric. Alright, that gets rid of mu, and we'll put the mu up there, so mu will disappear, and mu will go up here, over here, and which is what happens down on the next line. And this object with the Kronecker delta, because lambda and mu must be equal to each other, mu goes up here in its place. And we're left with this object in brackets, which we will call g lambda mu, and we will see next page over that this is called the Einstein Tensor, and has a very important role in general relativity, lies at the heart of the theory. By contracting the Bianchi identities and using the symmetry properties of Riemann Tensor, we've created a new tensor. We've made up a new one, known as the Einstein Tensor. This tensor is also symmetric, just as the Ricci Tensor is.